Okay, so based on this, we can do a similar thing that we were doing with electric force, but with electric field. So if you see, for instance, in the diagram, let's go ahead and do 19A. A. I'm going to call this R1 and that R2. Does that work? So we want to find what is the strength of the E field at point P. First of all, what would our E fields relatively look like between these guys? We would have E field lines running this way, right? And of course, many more coming out of him than going into the other. Correct? So, think about what is going to be the direction of the E field right here. Where's it going to point? It's going to point in this direction, right? Would you all agree? Would you agree that both of them are contributing the E field in that direction? Yes, because the lines go into the negative and out of the positive, right? Yes? All right, so really there's two E fields, like two causations of that E field, right? So to find the E field at any point due to point charges, we will use this equation. K sigma Qi over Ri squared. Now what does that mean to us? The sum of all the charges involved divided by all those individual charges, individual distances, right? So in other words, that would be like saying this. That would be like saying KQ1 over R1 squared plus KQ2 over R2 squared. Y'all, in terms of this being 1 and this being 2. Would y'all agree with me? Would you agree that they need to be in the same direction? What is something that we can always remind ourselves to do so that we don't screw with the direction and that we get the right direction out of this just by thinking of it with logic? Don't use the sign of the charge of these, okay? Don't use the sign of the charge. If you're logically drawing it out and thinking about the direction, that's going to be more effective. Y'all see what I mean? Had this been a negative and a negative, then I would know that he would have an E field stronger than him pulling this way, and I could find the difference in them. Do y'all understand what I mean? I don't need to put in their charges as negative or positive. I can determine the direction based on understanding where the E field will point. Y'all follow me on that? All right, so let's go ahead and solve this guy. Let's go ahead and solve this guy. It's good redundant. Can we just say that this is going to work? Yeah. You all handle that? Because I hate plugging in all the numbers. It just wastes time. You will be asked to do that, though, so make sure that you can. Okay? Yes? There's an online closing Sunday, and it is closing Sunday. Two of the problems on there are quite challenging.
Is that the online from last?
Yeah, it's the one that I extended, yes. The one you had already worked on that you said there was a tough problem. I did a video to both of those tough problems, and I'm going to send a reminder about that, okay? I'm now going to show you about those kinds of tough problems right now, all right? So most of it is just points. You're having to think of them that way. You're having to break them into vectors, okay? You don't need to do that. You need to practice doing that. That's not the difficult part of this unit, so we got to be able to do that, no problem. Let's do one more kind of basic example, and then I'll show you the key thing for today. I want you, let's me give you which problems I want y'all to do still from this. Okay, so the next problems that I need you to do from this are on the homework page 132. That's the front. I just need you to do 12, which I think we already did, and 14. Okay? Then, on the next page, 133, I need you to do 18, 19D only, because those take forever, so we leave that one in fun. And then 20. All right? Then on 134, 21 and 22. And that's going to get us up to where we need to be before we get into Gauss stuff, okay? So I'll give you till Tuesday to have all those done on a separate sheet of paper, all right? Does that work? Yes. That's not that many problems. That's like 7 problems. All right. Now I want to talk about one of these. Let's actually do let's do 21. Okay, let's look at 21. So it's got that's on page 134. It's got a proton launched through a field. I'm not going to actually plug in numbers here. I just want to talk about it fundamentally. What are these lines representing? What are they drawing for us?
Electric field.
That's an electric field. So we've got this uniform electric field produced. Can somebody tell me what this electric field might have been produced by? How can you get an electric field to look like that?
Parallel plate.
Parallel plates. And we'll get into that later, don't worry. But yeah, to produce a uniform field like this, you could actually do something pretty clever. You could have a line of charges down here. What sign would be the charges down here?
Positive.
Positive charges, right? And you could have a line of negative charges up here, and you know those E-field lines would go straight from one to the other, right? At least inside. When we're talking about in between the plates, we're not going to worry about what is called fringe effects out here. We'll get into that later. But anyhow, so you get this nice uniform E-field. What I mean by uniform is the distance between these E-field lines isn't changing as you move through it. You notice how from a point charge, we notice immediately from a point charge, what's happening to the distance between those E-field lines, the density between them. It's getting less, right? That's because as you get further away, the E-field is getting weaker. Because the lines are spreading out further. It all has to do with that geometry. Y'all see what I mean? Now, in this case, as long as we're inside here, does the density between the lines change? So this is what we call a uniform E-field. Uniform meaning that it doesn't change in strength inside there. Y'all see what I mean? Normally, an E-field gets weaker if you get further away. Well, that's due to the geometry of the E-field line itself. Okay? So, in this problem, they shoot a proton into one of these uniform E-fields. So it's got some velocity, it's launched in there somehow. And we want to talk about a few things here. So, first off, this is on Earth, okay? So we're going to be on Earth. Normally, what would any object launched, if I were to throw it straight forward, do? It'd fall in an arc path, correct? That's obviously because there's what kind of force acting on it? Yeah, if it's got mass, it must have a force of gravity on it, right? I mean, it's a little mass. It's about as little mass as you can get. But it's got mass, right? So it does have a force of gravity. It would fall, okay? Now, once it starts entering that E-field, it too experiences, so I'm going to draw it now in the E-field, like just entering it. So it experiences a force also because when you put a charge, when a charge is exposed to an electric field, you get a force. See that equation? E is the force of electrostatic divided by Q. Well, that means that force is E times Q as well. Y'all understand what I mean? Now, is there a force if no charge is in that field? I mean, not at least on the charge. There might be some force between plates, but they're probably being held there in position. But yeah, so the force starts to exist once a charge is exposed to the field, right? It's like that field was there waiting to act on something. Just like right now in this room, the gravity field is sitting here waiting to act on something. As soon as I put a charge, a mass into the field, boom, it exerts a force and it acts, right? It's the same thing. It's like this room has a big electric field. We put a charge in it. It's going to experience a force due to that electric field because of its charge, right? Can anybody tell me what's going to be the direction of that force on this charge based on this orientation?
Up.
How do you know?
Because it's a positive charge.
So he's going to want to go towards the negative. Well, what if I didn't tell you there was negatives up there or positives down here? Because the problem technically doesn't tell you anything about that.
The arrows.
It's the direction of the E field lines, right? Positive charges are always going to go in the direction of an E field line. At least the force they're going to feel is going to be in that direction. Does that make sense? So what does that mean about negative charges that we have to watch out for? Negative charges are attracted. They want to experience a force opposite the direction of E field lines. Yes? Okay. So anyhow, so that guy goes in there. mg is its force of gravity. And then this is its electrostatic force. How would we find electrostatic force if it's a uniform E field? Do we have to do kq over r squared? No, we can't do kq over r squared. It's not from a point or a sphere. We actually have to just say EQ. Y'all see what I mean? So that's A and B. What would be the direction? Oh, well, and then ask for the magnitude. Right? So A, B, C, and D. E, what will be the velocity of this proton 1.25 milliseconds after entering? So let me ask you right now, what's going to happen to the velocity of this proton if, and this is to assume, if we're able to have, we don't know which one's greater actually, that's part of the problem, is you find maybe they're the same, maybe one's greater than the other. Okay? So assuming, let's say this, assuming they're equal to each other, what's going to be the effect on the velocity? There isn't going to be one, right? If those two forces would be equal, wouldn't that guy just keep moving straight through that thing? Do y'all understand that notion? Now, what if one of these forces was greater than the other? Let's say that this guy turns out to be stronger, which is easy to do, by the way, to make the electrostatic force stronger than gravity on a small particle. What if that electrostatic force was stronger? What would we see this particle do? And where would he crash? He'd crash into the upper plate at some point. Look what he looks like. His path would look like. It'd be like a projectile, right? It'd be like a projectile. So what you can do is find the acceleration there, and that acceleration is only acting on the y-axis, so that you can find, its change in velocity at that point. You can treat it like a projectile. You all see what I mean? Okay. And you can do the problem and work that out. I just want to clear up that idea. All right, so here's another notion that we're going to do is, all right, so for multiple point charges, E field for multi-charges is K sigma Qi over Ri squared. We understand what that means now, right? We did one of those. Okay. So, can anybody tell me if I had an extended body of charge? That's where it gets fun, boys. There we go. I respect it. Okay. So if we get into like extended bodies of charge that aren't just points, now we're getting back into some juicy territory. Hold your horses with that term. We aren't even gonna whisper it again for another 2 or 3 weeks, okay? All right, cool. All right. He is excited about capacitors. We will get there, I promise. All right, so, yeah, we got extended body of charge, okay? So guess what a sigma turns into when you got an extended body of charge, meaning that it's an E field due to a bunch of charges making up a solid shape. Oh. And guess what our Q is going to be? So imagine having this thing as a big ball of charge. Couldn't we pretend that this big ball of charge is made up of a bunch of little charges? Little charges? What are those little tiny things called? They're called elements. Yeah, they're little infinitesimal pieces, right? We'll call them DQs. That's what I like about physics. Yeah. Yeah. So now, guess what? It's all about the distribution. How are these little DQs distributed in terms of where our location of E field that we want to assess? These are called, you ready? Charge elements. Everybody say that. Charge elements. Charge elements. Yay, little tiny little pieces of charge. Okay, charge elements. Cool. And what happens when you integrate DQ? It becomes the whole charge of the object. The integral of DQ is Q. Now, that's not always going to be your integral. It's not going to just be that simple, because sometimes it's going to be distributed in a way where we need to assess not about the whole charge, but about the effect of the E field due to some of the charge being over here, some of the charge being down here, and I want to know what the E field is here. You see what I mean? At that point, we have to get charge as an expression of something else. So, bum. Welcome back to density. Charge density. Yeah! Now, we usually think of density in terms of what? Mass density, right? When we talk about density, we're talking about mass density. But mass is very, very stingy. Density doesn't have to apply to mass. It can apply to any fundamental component. Charge is a fundamental property of mass. Things have mass and they have charge. Those are things that define atoms, right? Their charge and their mass. Those are defining things of any fundamental building block. So charge is just as fundamental as mass is. Okay? So charge density. Guess what kinds of charge density we're going to have? Linear, area, and volume.
Attention Brandeis, at the bell we release students to their second period class. Teachers, if you need additional campus report cards, please collect those from Kim Teal in the counseling office. If you are short campus report cards, you may retrieve those from Kim Teal in the counseling office and distribute to your students who are in need of them on Monday.
Great.
Students, if you have a second period PE class, you are to meet in the locker room area.
They're going to ring the bells.
We will
send y'all to your second period. Great. Well, now, do these look familiar?
Yes.
Yeah, except it's Q instead of mass, right? So check
Teachers,
this
you will
out.
also report to your assigned second period class.
Okay. So, in terms of infinitesimals, this becomes dq dl. This becomes dq dA. And this becomes dq dV. Well, y'all got off the hook on this. I changed my mind. Again, the online will be extended further. Those problems that I wanted you to do, that I had you circle, are due Monday. Do not worry about the online if you don't want to, okay? All right, have a good one. Actually do them, those of you who have not. And some of this work was pretty phony baloney to me. Come on, guys, this isn't that bad yet.
I'll get you that one copy of my work. I'll just rewrite it on another sheet of paper.
Okay. If you're in second period, you need to grab one of those. Daniel John, right? All last name is with a J. That puts you O-P. Oh, John, there you go. All right. Take one of those. Kathleen Klein, there you go. Which one is